Okay, so today we are going to see principal component analysis, and we will see that how there are two objectives in principal component analysis. The first one is variance maximization, and the second one is reconstruction error minimization. So we will see that how both of these objectives are achieved in principal component analysis. Now, what is dimensionality reduction? Right, first of all, the thing that is, what is dimensionality reduction? So dimensionality reduction or means basically that we reduce the number of dimensions in our data set so as preserving maximum amount of information, because visualizing a higher dimension data set is computationally expensive. Working with higher dimensions is computationally expensive. So therefore we want to project our whole data into a smaller number of dimensions. Now, why do we need dimensionality reduction is what we saw. So dimensionality reduction is an unsupervised learning problem. Now, what is unsupervised learning problem? We are having a data set that are not having labels in the case of unsupervised learning. And by that we try to find hidden patterns in the data set, or we want to find the outliers. Okay, so now dimensionality reduction, right? So let us consider that we are having a data set of motorcycles, and there are many attributes like color, maximum speed, engine power, etc. Now imagine that there are two columns, and both of them are basically, one is speed in miles per hour and one is speed in kilometer per hour. So we can say that in place of these two different attributes, we can have only one attribute, and that is just the speed, right? So the dimension naturally reduces by 1, because we have in place of two dimensions we have taken only one dimension. Now see, another thing that we can imagine here from here is, let us consider that we are having a house price prediction data set with columns like number of number of rooms, number of washrooms, and number of grocery shops nearby, and we want to predict the price of the property. So by our common sense we can say that the price of property does not very strongly depend upon the number of grocery shops nearby. So what we can do here is, we can select only two relevant features and drop the third one. So this is feature selection. Now among that two features, the first feature is basically number of washrooms, the second is number of rooms. So what if I club both of them and form a new feature, that is basically floor area, right? So floor area will be depending floor area will be depicting the information that is being conveyed by these two features. Now again, coming to the iris flower dataset, here also we are having two features like sepal width, sepal length, etc. And since length and width grow in proportions, right? If the length increases, the width also increases. So in place of these two, we can replace it with a term like feature like sepal size. We will see it again later. For the time being, now what is dimensionality reduction mathematically? So it is basically a mapping of a higher dimensional data set to a lower dimensional data set. So we are mapping it using a function f, and the theta is the parameters. Theta is the parameters that help us to map the set x to set z. Now the set z should have lower dimension compared to the set x. So here we are seeing this, that if our x is coming from the set of real numbers and it has dimensions d, and if our z is coming from set of real numbers with dimensions p, then for some p less than d, then the transformation f theta, which gives x, which takes input as x and gives output as z, is a linear function with parameters theta is equal to coming from real numbers and of the order of d cross p. Why it is d cross p? Because what we are going to say is the formula will be z is equal to f theta x, that is equal to wt x. So w is our matrix, that is our parameter theta. So when I want to obtain z, what I am doing is I am taking the transpose of w and multiplying taking the dot product with the x. So see, there are two very interesting examples that we will take here. The first one is learning the pattern, learning the trying to decipher the various numbers that are written using an unsupervised learning method. So what it says basically, see, 1 can be written in 2 ways, 2 can be written in 2 ways here, 6 can be written in 3 ways. So 1 and 1 form clusters, but they are closer, right? They are closer together. Similarly 2, similarly for 6. So that means in unsupervised learning algorithms, without knowing anything beforehand, our algorithm predicts a pattern or find clusters here that are more likely to be related, so they will be nearby. Now coming to another very interesting application, that is DNA analysis. See, we are having the genome, we are having the DNA of particular geographical areas, right? In Europe, we don't have the map, just we have the DNA sequencing for all of the country of Europe. If I plot it and take this axis like PC1 and PC2, these are the axes where the variance is maximum. Later we will see that we are basically calling them as principal component 1 and principal component 2. So the variance is maximum among this, and this particular DNA sequence map just resembles the actual geographical map. Now why it is happening is because persons that are tend to be closer geographically are more, the probability of having them kids increases. So the common sense, we can say that those who live nearby, they will only participate in creating offsprings. Now principal component analysis. So principal component analysis is a dimensionality reduction method. It is a dimensionality reduction method in which we are what we are doing, we are projecting our data to a lower dimension. So components of an unsupervised learning algorithm is a data set plus learning algorithm gives unsupervised model. Now learning algorithm may have model class. So model class basically means k-means or PCA, whatever we are going to take. Objective means the loss function that we are going to take, and optimizer means the algorithm that we are going to use for achieving this objective. It may be a gradient descent, right? So coming to the next part and now seeing the assumptions of the PCA model. So the first assumption is that X belongs to RD lives close to a low dimensional subspace Z is equal to real number of P of dimensions P dash T. That means let us imagine that there is a 3D space, and inside it there is a seat of 2D seat, okay, and there are, let us say it is a suite or something like this. So a swarm of honeybees are sitting on this particular seat. Now what if I want to predict the exact data here? So I want to see actually the position of these honeybees. So I don't need to work in this 3D, rather I can just take this 2D diagram and assign some coordinate axis, and with respect to that coordinate axis I can measure the positions of these honeybees. Okay, so this is the second point. The subspace Z is equal to R to the power P. Rp is spanned by a set of orthonormal vectors W1, W2 and Wp, and the data X are approximated by linear combination of, that means how the X will be created. So first of all we saw that Z will be created by the projected data will be created by multiplying W transpose with X. And now if I want to again recover my X, So the formula that we can use is mm, W of W transpose X or W of Z for k is equal to 1 to p, right? So these are the three assumptions, and this is the diagram. Now see, this yellow this blue plane is the plane about which we are talking. So we can project it into a 2D and we can see the data points there. Now the model for PCA. For PCA, what is the function? Model means what? Model means basically the function. So it is going to be W transpose X. Z is equal to W transpose X. Now there can be two tasks that the model enables. The first one is encoding. That means it is creating Z out of X. So Z is equal to W transpose X. Now decoding means going back to higher dimensions, right? So X component is X tilde is equal to W times of Z. Now moving to the PCA objective that we were talking initially. So the first one is reconstruction. So what is meant by reconstruction? By reconstruction I mean that I am going to take the L2 norm of the actual value of X minus the predicted value of X, right? The restored value of X. So we are writing it as Xi minus Xi tilde 2 2. The upper subscript 2 stands for squaring. So if I want to write the J1W or the reconstruction error, the objective function here is going to be I is equal to 1 to n xi minus xi tilde square. Now for xi tilde I can write it as WWT xi. Between each xi and its approximate reconstruction I can write xi is nothing but WW transpose xi, right? So this is my first reconstruction error. Now coming to maximizing the variance. So what it says, an alternative objective for learning a PCA model is maximizing variance. So let us see that iris dataset again, and here you can see that if I take this particular axis as my principal component, then I am getting the maximum variation. That means it is able to capture the pattern of maximum amount of data, and the perpendicular one, because they need to be orthogonal, so the perpendicular one is not able to catch or capture that much amount of data. We will again see this particular data, and then we will see that how we can derive maximum variance. So if I draw the line like this, it is too clustered, right? And if I draw the line like this, then it is too large. That means it is good for us. Now coming to the next thing, that is what is the empirical expectation. So empirical expectation E cap of f of x is nothing but the average. So assume that we have centered the data. Now once we centered the data, so expectation of x will be equal to 0. Why? Because it is basically mu, and since you are centering the data, that means you are already setting the mu to be 0. Okay, here one thing you should note is expectation of W transpose x is equal to W transpose times of expectation of x. Why? Because W transpose is a constant part that comes outside. Now the variance of the projected data. So what will be the variance of projected data? E hat z minus expectation of z square. So expectation of z square, z is basically WTX and z is WTX. So expectation of WTX is 0, we saw here. So it will be finally just W2TX square. Okay. So this is the variance of the projected data. Thus the variance objective is simply J2W is equal to E hat WTX square. E hat WTX square. And so here what we were seeing, it is E of WTX square, that is 1 by n W2T xi and 2 2. So equivalence between the PCA objectives, right? So it turns out that minimizing reconstruction error and maximizing variance are equivalent. Now let us see this. So consider the operator W transpose x. We can decompose any x into a sum of two orthogonal vectors. So x plus W transpose x minus W transpose x. So we can write here as W transpose x as projected data D1 and I minus W t x is equal to difference between the data point x and x1. So data point and the projected point d2. So it is the distance I minus w transpose x, and the projected in d1 is w transpose x. We can compute the norm of both the sides. So using Pythagoras theorem, as we saw that since these two axes will be perpendicular to each other, this will be perpendicular because we are trying to measure distance. So I can write d1 square plus d2 square is equal to d3 square. d3 remains constant. So what I can write from here, mode of L2 norm of x is equal to w transpose x plus I minus w transpose x. Now I can take it individually. So w transpose x 2 plus I minus w transpose x 2. Now w transpose x, what will happen? Because since they are orthogonal vectors, the w of x, since they are orthogonal vectors, I will show you that how I can write that particular thing. Okay, so let us start with this. W transpose of x. So what I'm going to show you is, here it is written w of w transpose x, right? Let me change the pen color. Okay, so and you want to find the L2 norm of this. We also know that w transpose is equal to w inverse here. Why? Because they are orthogonal. So w of w transpose x is equal to w of w inverse x, and w inverse is equal to I, so it will be I only, it will be x only, right? So what we saw, that w transpose x is simply written as w transpose x is simply written as w of is simply written as a. Why? Because these two things will club to form x. Okay, so here you are getting x simply, right? So now if you are getting x simply, so you can write here that this is equal to x of L2 norm of the x. So this is the thing that is done here in this particular step. Now applying Pythagoras theorem, I can write w transpose of x L2 norm and then L2 norm of I minus w transpose x. Since they form a right angle triangle, therefore the Pythagoras theorem was applied to it. Now coming to the next thing, that is the second of our objective was to maximize the variance. So what I can write here, I is equal to 1 to n I minus w transpose xi to 2. Okay, xi to 2. So from here I can write that x I L2 norm minus wt xi L2 norm. So what this will give you, xi the norm will give you constant, and then w transpose x will be equal to minus of n times of j to w. Why n? Because if one by n is multiplied there, and then it will be basically the j to w. Okay, so we saw that minimizing the reconstruction objective J1 is same as maximizing the area objective. Thank you.